Hello everyone and welcome to my presentation. Let me start by saying few words about my own background. I, Raman, Assistant Professor in Mechanical Engineering Department, IIMT College of Engineering, Greater Noida. As you can see in the screen, our topic is theories of failure. When we are talking about theories of failure, first of all, we understand why we need these theories of failure. As we know that in the machine component there are different materials used for the making of that component, and there are different kinds of stresses or forces uh, applied on the component, and because of that forces there are different stresses induced on that component. So that material is have enough strength, then that machine component is good. Otherwise, it may get fail because of the stress which is not supported by the material. As we can see on the screen, the failure theory is a criterion that is used in an effort to predict the failure of a given material when subjected to complex stress conditions. So in this section, we will discuss about five theories of failure which are used in engineering practice for the making of mechanical engineering component, and that is subjected to complex state of stress. So, for example, if you see this mechanical component, then you can see this has to be failed because of the stress induced, and that stress is not supported by this material of the component. So, before going to understand this theories of failure, first of all, we understand about the properties of material. First of all, we would find out the properties of material that is used for the making of component. So, for that reason, first of all, we would make the standard specimen for the material which is used for the making of a component, and that standard specimen is tested on this UTM machine, and after the completion of this test we can get the stress strain diagram, and on that basis we can find the maximum value of stress that can be sustained by the materials. As you can see in this stress strain diagram, as we can see on the y-axis that is there is stress, and on the x-axis there is strain, and up to the yield strength that curve is straight line. As in the straight line, you can see that stress is directly to strain. And after yield point, that curve is going to deviate and ultimately will get fail because the material is not supported the further load. So from this stress strain diagram, we can get the properties of material, we can get the maximum value of the stress that can be sustained by the materials. So there are different scientists, they are produced different theories of failure, and if we are going to make the component, we can use any one of theory among all these five theories. So this first theory is maximum principal stress theory. Second is maximum shear stress theory. Third is maximum principal strain theory, and then total strain energy theory, and then distortion energy theory. When we are talking about all these five theories of failure, in these five theories of failures, whatever the forces acting on the component, we would find out the values of stress, values of principal stress, values of shear stress, values of principal strain, and then total strain energy and total distortion energy. All these theories, all these values can be compared with the values when we perform the UTM machine. So now let's start one by one theory. So first theory is maximum principal stress theory. This theory states that the failure of a mechanical component subjected to biaxial or triaxial stresses when the maximum principal stress at any point in the component reaches the maximum principal stress in simple tensile test. That means whatever the mechanical component we are going to make, whatever the forces applied on that component, and because of that forces, stresses induced on that component, so we have to calculate the value of principal stress, maximum principal stress, minimum principal stress. So let sigma 1 and sigma 2 are the two principal stresses at a point in the component, either sigma 1 is greater than sigma 2 or sigma 2 is greater than sigma 1. So if we apply this theories of failure according to this theory, if sigma 1 is greater than sigma 2, then if we increases the load, increases the force, the sigma 1 is also going to increase. If the sigma 1 reaches to the yield strength of the material, positive is for tensile stress and negative is for compressive stress. If sigma 1 reaches to sigma yt, then component is going to fail. If sigma 2 reaches to sigma yt, then component is going to fail. So in these two equations, we can see that sigma 1 or sigma 2 are the variables and sigma yt are the constant value. That means it is the property of the material, so it is constant value. So this two equation is the equation of a straight line. Two equation is for tensile and two equation is for compressive stress. So on the basis of all these four straight line equation, we can make the safety regions in which we can see in this figure on sigma 1, because sigma 1 and sigma 2 are the two principal stresses and they are mutually perpendicular to each other. So on the sigma 1 line, sigma 1 for tensile, the maximum value is sigma y2, and for the compressive value, its maximum value is minus sigma y2. And if you are talking about the sigma 2, then sigma yt is maximum value is of sigma 2 is sigma yt for tensile, and maximum value of sigma 2 is minus sigma yt for compressive. So if the values of the stresses, principal stresses of that component lies within this region, then that component is safe. If the value of this stresses falls below these regions, then our component is going to be fail, or we can say that component is not of the use of particular applications. Next is maximum shear stress theory. This theory states that the failure of the mechanical components subjected to biaxial or triaxial stresses occurs when the maximum shear stress at any point in the component become equal to the maximum shear stress in the standard specimen in simple tensile test. So once again, we are going to say that whatever the forces induced on the component, acting on the component, and because of that forces, the stresses induced on the component. So we have to calculate the value of principal stresses sigma 1, sigma 2, and sigma 3, which are three principal stresses, and all these three principal stresses are mutually perpendicular to each other. So by with the use of this sigma 1, sigma 2, sigma 3, we can calculate the value of maximum shear stress. So maximum shear stress for this triaxial stress system, sigma 1 minus sigma 2 by 2, or sigma 2 minus sigma 3 by 2, or sigma 3 minus sigma 1 by 2. These are the three shear stresses, and among all these three shear stresses, which one is maximum, we have to compare this with the standard specimen test. And for if we are talking about biaxial stress system, then maximum shear stress is sigma 1 minus sigma 2 by 2, or sigma 2 by 2, or sigma 1 by 2. That is plus minus sigma 2 by 2 or plus minus sigma 1 by 2. And for uniaxial shear stress, the value of maximum shear stress is sigma 1 by 2. If the standard specimen perform the test on the UTM machine, then that component is going to fail when sigma 1 reaches to sigma 1. So for that, the maximum shear stress is sigma 2 by sigma yt by 2. So according to this theory, for triaxial state system, sigma 1 minus sigma 2 is equal to plus or minus sigma yt, plus for tensile and minus for compression. Or sigma 2 minus sigma 3 is equal to plus minus sigma yt, or sigma 3 minus sigma 1 is equal to plus minus sigma yt. These are the six equations. And if you are talking about the biaxial stress system, then sigma 1 minus sigma 2 is equal to plus or minus sigma yt, sigma 2 is equal to plus or minus sigma yt, or sigma 1 is equal to plus or minus sigma yt. So among all these six equations for biaxial stress system, which one is maximum? The component we are compare it with the standard specimen, test on lithium machine, and use that equation for making our component or for the selection of the material for that particular applications. So third theory is maximum strain theory. In this maximum strain theory, this theory states that the yielding at a point in the material begins when the maximum strain corresponding to complex state of stress exceeds the maximum strain corresponding to yield point in simple tensile case. That means whatever we are first we are going to select the material and make the standard specimen, perform the test on lithium machine and find the results. That means at the time of failure of that standard specimen we have to find the value of maximum strain, and then we use that material for the particular component for the particular machines, and whatever the forces acting on that component we have to calculate the principal stresses which is acting on that component, and if that on the basis of that principal stresses sigma 1, sigma 2 and sigma 3, we have to compare it with the standard that standard specimen test on the UTM machine. So for triaxial stress system, there are also six equations we can get. One is sigma 1 minus mu sigma 2 is equal to plus sigma yt, and sigma 1 minus mu sigma 2 is equal to minus sigma yt. These are two equations. Similarly, sigma 2 minus mu sigma 3 is equal to plus or minus sigma yt, and sigma 3 minus mu sigma 1 is equal to plus or minus sigma yt. Here sigma 2, sigma 1 and sigma 3 are the principal stresses. Sigma yt is the value of the yield strength. That means we can get it from the stress strain diagram, and mu is the value of the Poisson's ratio of that component. For biaxial stress system, if the value of sigma 3 is equal to 0, so we can get four equations. Sigma 1 minus mu sigma 2 is equal to plus sigma yt, sigma 1 minus mu sigma 2 is equal to minus sigma yt. Similarly, if sigma 2 is greater than sigma 1, so sigma 2 minus mu sigma 1 is equal to plus sigma yt or minus sigma yt. So we can draw the safe region for biaxial stress system, as we know that sigma 1 and sigma 2 are the two mutually perpendicular stress, and they are and sigma 1 is on, if sigma 1 is maximum, so sigma 1 is on x-axis and sigma 2 is on y-axis. So these are the four equations, and these four equations sigma 1 sigma 2 are the variables, and mu and sigma yt are the sigma yt is the constants. So all these four equations also represent the equation of straight line. So we can, with the help of these four equations, we can draw the safe region, as here we can see that on the graph and figure. One line is this one, another one is these four equations. The bounded region with the help of these four equations is the equation of safe region. That means the value, whatever the value of the stresses used in that component, if that values lies within this region, then our component is safe. Otherwise, the component is not used for the particular purpose. Next is total strain energy theory. When we are talking about this total strain energy theory, this theory states that the yielding at a point in a material begins only when the energy per unit volume absorbed at the point is equal to the energy under the uniaxial state of stress. That means in simple tensile test, as in the case of simple tensile test. So again, we are saying that whatever the material we are selected, first we uh, make the standard specimen, then perform the test and find the results at the time of schedule. We can get the total strain energy, or we can say we can get the yield strength, or ultimate tensile strength, or fracture strength, and when we use that material for the particular component, then whatever the forces acting on the component, we can calculate the value of the principal stresses sigma 1, sigma 2, sigma 3, and with the help of this sigma 1, sigma 2, sigma 3, we can find the result. We can get the equations for tri-axial stress system, sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu, where this mu is the value of Poisson's ratio of that material. So minus 2 mu in bracket sigma 1 into sigma 2 plus sigma 2 into sigma 3 plus sigma 3 into sigma 1 is equal to sigma yt square. This is after the comparison of particular system and for the standard system. And when we are talking about the biaxial stress system, sigma 1 square, you can get the equation sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 is equal to sigma yt square. This equation used for both either tensile stress system or for compressive stress. So if we are saying for biaxial stress system as for triaxial system stress system, the figure is on three dimensional. So that is impossible to show on this 2D diagram. So for biaxial stress system, we can see that this equation sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 is equal to sigma yt square. This equation represents the equation of ellipse where the 155 degree from sigma 1 axis on anti-clockwise direction, that is the major principal axis, and from sigma 2 at 45 degree from anti-clockwise direction, that is minor principal axis. So on this major principal axis and minor principal axis, by putting the different values, we can find the safe region, as this green region is bounded by this equation sigma 1 square plus sigma 2 square plus minus 2 mu sigma 1 sigma 2 is equal to sigma yt square. So this is the equation, and value of whatever the stresses on that component induced, if that stresses is lies within this region, then component is safe. Otherwise, it may get fail, or that component is not of use for the particular purpose. Now the last theory is distortion energy theory. This theory states that the yielding at a point in a material begins only when the strain energy of distortion per unit volume absorbed at a point is equal to the strain energy of distortion per unit volume corresponding to yield point stress in simple tensile test. Same thing in this also, but here we are using distortion energy. So again, for the particular component, whatever the stresses induced on the component, we can calculate the value of principal stresses, sigma 1, sigma 2, and sigma 3. These are the three principal stresses. After calculating the sigma 1, sigma 2, sigma 3, for triaxial system, we can make the equation sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is equal to 2 sigma yt square. And for biaxial stress system, sigma 1 square plus sigma 2 square, that means we have to put the value of sigma 3 is equal to 0. So we can get the equation sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2 is equal to sigma y2 square. So this equation also represents the equation of physics. So in this, we can also say that if a designer want to design a component, they can use the value of factor of safety, and that factor, use of that factor of safety is uh, by dividing the sigma y2, that means yield still by factor of safety. We put this value on the equations and we can design the component for safety. So for this elliptical shape, elliptical since this equation represents the equation of physics, and also on 45 degree in anti-clockwise direction from sigma 1 line, sigma 1 axis, it is major principal axis, and again at 90 degree that uh, major minor principal axis. So this equation, this green region represent the safe region, and the value of the stasis, if that value lies within this region, then our component is safe. Otherwise, the component is of not zero. So overall, we can say that if designer want to design component, then they are or they always use any one of these theories of failure among all these five theories of failure for designing the component, and always they are trying to use factor of safety also, and that factor of safety may be 2 times, maybe 1.5 times, 3 times, that depends upon the harmfulness of the situations they are using it. So this is all about the theories of failure. Thank you.